This video presents our paper on Adversarial Training and Robustness for Multiple Perturbations, which appears at NeurIPS 2019. We tackle the problem of defending machine learning models against multiple types of adversarial examples. We show, both formally and experimentally, the existence of a robustness trade-off, where defending against multiple perturbation types lowers the model's robustness to each individual type. We also introduce affine attacks that further reduce the accuracy of robust models by interpolating between perturbations. So what are adversarial examples? They are minimally perturbed inputs that reliably cause classifiers to make mistakes. These failures show that machine learning models learn very different features than our own visual system and are a concern for safety or security critical deployments. A natural defense against adversarial examples is adversarial training. For some chosen sets of perturbations that we want to be robust to, we continuously generate worst-case adversarial perturbations for our model and add these to the training set. Adversarial training does improve robustness for the type of perturbations that the model is trained against, L-infinity noise in this case, but the model remains vulnerable to other types of perceptually small perturbations, such as sparse noise or small rotations. We thus ask whether we can extend adversarial training so as to learn a model that is simultaneously robust to multiple types of perturbations that an adversary might choose. We generalize adversarial training to this setting by training a model on worst-case adversarial examples that come from the union of all the chosen sets. So does this work? Yes, but with some interesting caveats. On CIFAR 10, for instance, we showed that the model trained to be robust to just two types of perturbations loses about 5% of robust accuracy compared to models that were individually trained against each perturbation type. We actually proved that this type of robustness trade-off is inherent in some natural classification tasks. Surprisingly, on MNIST the situation is even worse. A model trained on multiple types of LP noise achieves only about 50% robust accuracy, a drop of 20% compared to models individually trained on each type of noise. What's happening here is that to achieve L-infinity robustness, the model learns to threshold the input pixels, and this partially zeroes out the model's gradients. As a side effect, this breaks L1 and L2 attacks, and the model fails to learn a robust representation. Our work shows that this issue, commonly known as gradient masking, also affects adversarial training. Finally, we consider a more general adversary that combines perturbation types. As an example, we show that instead of either rotating an image or adding small noise to it, an adversary that does a little bit of both can further reduce a model's robust accuracy by 10%. To conclude, while we can train models against different types of adversarial examples, this comes at a cost in robustness to each individual type. Our work raises some open questions, such as how to prevent gradient masking on MNIST, or how to more efficiently scale multi-perturbation adversarial training. Finally, there remains the fundamental question of how to list all the types of perturbations that we want our models to be robust to in order to emulate our own visual system. If you'd like to learn more, we invite you to read our paper or to attend our spotlight talk and poster at NeurIPS.